Hello friends, this is Leetcode problem 441, arranging coins. This is also released as part of the July coding challenge problem number 1. We're given an input which is the number of coins n, and we need to arrange n coins in a staircase shape such that kth row contains exactly k coins. Given the input number of coins, we need to return the number of full rows that can be found. Let's work with some examples. Let's assume we're forming a staircase with one row, so it looks something like this. If it's two rows, it'll look something like this. So first row has one coin, second row has 2 coins, and third row has 3 coins. If we notice, the number of coins is 1 in the first case, it's 1 plus 2 in the second case, and it's 1 plus 2 plus 3 in the third case. So if we are given n rows, then the number of coins is the sum of numbers from 1 through n, which is calculated with the formula. First number of sum of first n numbers is n into n plus 1 by 2. In this problem, we are given the number of coins and we need to find the number of rows. If we are given n coins, then the number of rows possible are somewhere between 1 through n. We don't know the exact number, but it is monotonically increasing between 1 and n. So we can consider the range of possible values for rows is low is 1 and high is n. It's somewhere between that. Number of rows is in fact monotonically increasing between 1 and n. So we can consider this problem to be an equivalent binary search problem where low and high are 1 and n respectively. If we have n rows, then the number of coins is n into n plus 1 by 2. We've seen that earlier. So we can solve this problem as a binary search problem, searching for the number of rows which is between 1 and n. Let's see some code here. We'll initialize our low and high. We can run a binary search between low and high. We can initialize the answer variable which is to be returned. This is a binary search between integer indices. We want to protect ourselves against integer overflow, so we'll just take the midpoint, avoiding integer overflow. Now if we are given low and high are the number of rows. If you are given the number of rows, then the number of coins can easily be computed as the formula we saw earlier, which is n into n plus 1 by 2. Now this product can in fact overflow. Integer multiplied by integer can overflow into the long range, so we can wrap this into a long to avoid integer overflow problems. If the number of coins matches exactly the number of coins which is given as input, then we found the answer. And remember that this binary search is to find the number of rows. So low, high, and mid, they represent the number of rows. So when it comes to returning, we'll return the number of rows, which is in fact mid. a comparison is based on number of coins, but we are always going to return the number of rows. The other possibility is that the number of coins is less than total number of coins which is given as input. This means this is potentially a valid answer, so we save that. But this also means that we are searching on the lower side of that range between low and high, so we move to the higher half. So this means low is mid plus 1. Otherwise, if for that midpoint the number of coins is greater than n, then this is not a valid answer, so we'll not save it. But we'll shrink our search space to look at the lower half, which is high is mid minus 1. And that should be it. Again, to repeat, we run a binary search between low and high. This represents the number of rows, which can be monotonically increasing between 1 and n, the total number of coins. We compute again the midpoint, which is again the number of rows, get the number of coins for the number of rows mid, which is the sum of first n numbers, and if the number of coins is input, then we found an exact match and we return the row. If the number of coins is less than our target, then this is potentially answer, so we save that and we continue searching for a better answer by looking at the higher range. Otherwise, if the number of coins is more than the input, then this is not an answer. We shrink our search space to the lower half. It should be okay. Let's see, it's working fine. This is good. Let's submit this. Okay, we got it. So the complexity here is the binary search complexity, which is going to be log of n. So the time complexity is order of log of n, and we are not using any additional space, so the space complexity is constant O of 1. Thank you.